Welcome. Welcome. Anyway, welcome to the Berkeley Physics Department Colloquium. Today's speaker is Professor Reinhard Genzel. Reinhard received his PhD at the University of Bonn in 1978 and then went to the Center for Astrophysics at Harvard for his first postdoc, and fortunately came here to Berkeley in 1980 for his second postdoc. He was a Miller Fellow. He was then on our faculty from 81 to 85. Then he became a director of the Max Planck Institute for Extraterrestrial Physics in Munich in 1986, and continues as a director there. Fortunately for us, we were able to lure him back, and he got a 25% appointment in the physics department from 1999 to 2016. And I used to call him the 125% man because he had to do 100% of the time more just to be a director of the Max Planck Institute with a large group. Plus, he would then spend a couple months here each year. So we were very fortunate to have him there, and now we're fortunate to have him back again. Of course, he has won many prizes. I would mention the first one being the Miller postdoc he got here. Then he got the Newton Plessy Pierce Prize for the American Astronautical Society, the Quayforth Prize, which actually used to be known as the Nobel Prize for Astronomy, because for a long time the Nobel Prize was not given in astronomy. But then he did actually get the actual Nobel Prize for his discovery of a supermassive black object at the center of our galaxy. So today it gives me great pleasure to introduce Reinhard Genzel to give us a talk on black holes, now in the future. Reinhard.
It's so wonderful to be back home. Things have been changing lately, though. Let's not talk about it. I should tell you the story before I get into the center of the matter, that I stood here 44 years ago, and I then gave my introductory lecture as newly minted faculty, and you know, that's where Emilio Segre sat, Charlie Towns there, and old Owen Chamberlain there. Now, I had picked as my subject of the talk interstellar masers, water masers. That's the subject I worked on in my PhD thesis and also at Harvard in order to use a very long baseline interferometry to see the motions of little teeny specks of interstellar material, very dense, flying through interstellar space, and from that learning something about, you know, how in star-forming regions material gets ejected outward. So I was here, just right here, and starting to talk, and after 10 minutes, Emilio Segre pumped up and said, "What is this nonsense?" And yeah, was machen jetzt? And then Towns looked over at him. And then Emilio said, "You know, in interstellar space, there are no mirrors. So how can you have a reflecting cavity for a maser? This is complete nonsense, typical astronomy." And then, fortunately, Towns was there. Towns said, "Well, let's see now, Emilio. You have to understand." So, you know how he would do this, right? He would lead Emilio down into the basement, and then below the basement into the sub-basement, and at the end, Emilio was, and the topic was, okay, I could talk about masers. Whew. That's the kind of thing you experience in this wonderful hall. But indeed, today I will talk about something which has a lot to do with Charlie's work. namely interferometry. Now, back then, of course, the word on the street was the only one in the world who was able to make a optical stellar interferometer workable, so that you get, basically interfere the light from the edges of the telescope, or as you see in this case, from this long extension with little prisms in there that reflect the light to the center into the telescope, then you interfere it and get fringes, Michelson fringes. And from that you can say something about the size of the source, Michelson interferometry. But the thing is, in the textbook it says the only one who ever got Michelson interferometry in the optical to work was Albert Michelson. Nobody else. Pease, his successor, already failed. And so then, basically, for many years, nobody tried. Much too difficult. Yes, the radio astronomers can do this. Well, the radio astronomy, these big waves, but optical, that's it. Now, Towns, of course, knew there were other ways to do this, and so he built the second, if you like, route toward short wavelength interferometry by using the trick of heterodyning. So basically, instead of interfering the light of the two telescopes or three directly, he would first take the signals, the electromagnetic field strength, take a laser light, coherent laser light, in his case, a CO2 laser, and then, basically transform that into a microwave signal, and then combine the microwave signals from two, or in the end here, interferometers. Some of the heroes of interferometry are right there, and have made it possible that with that one could actually do what Michelson also had done, but now at 10 microns. But that's just the intro. Now, of course, as we think about black holes, first thing we have to put our minds to is, what do we mean by black holes? We mean really truly the event horizon predicted by the theory of Einstein. And the event horizon for a, say, 4 million solar mass black hole, like in the galactic center, is a radius of only 10 microarc seconds. 10 microarcs, and that's about this much on the moon. And no telescope in the world, until recently, was able to resolve this. But that's what we, in principle, would like to do. Yes, we can measure X-rays and gamma rays, and we can neutrinos and all of this. But that's all indirect information. As a physicist, experimental physicist, excuse me, as a simple experimental physicist, you would like to make a spatially resolved measurement of the event horizon. Isn't that what you would like to do? At least I. And so, so how do you do this? Not so simple, because in the optical, as I said, it was just barely possible. In the radio, it does work, and indeed, one of the measurements in the last few years where this was in fact used to make a near event horizon image of the galactic center was VLBI, the stuff I did as a thesis. But now, at very short wavelengths, 1.3 millimeters, barely possible for the atmosphere to transmit that, and many telescopes across the entire Earth, and that has a resolution of about 25 microarc seconds. So you can begin to sort of think, oh, there it is. And I'll show you what you can see with it, which gives you additional information. But then let's go back to the optical. That's, of course, where thermal radiation emerges. And if you want to look at the galactic center, you want to study the entire system. The black hole is one part of that story, which I will tell you about today, but also the central star cluster. And there should be, according to theory, a very dense concentration of stars near such a black hole. That was the theory worked out in the 1970s, and clearly predicted a very dense star cluster. Now, the problem in the case of the galactic center is it's very close, only 27,000 light years away, but as you see at this picture where the galactic center is, X marks the spot there, is all dark. And that's the effect of interstellar dust between us and the galactic center, dimming by a huge factor the optical light. So you cannot see the galactic center in the optical, but you can actually in the near infrared. And so with the enormous progress after the war, and then I should say after the Cold War, really, in infrared astronomy, and Charlie, again, was a great man helping behind the scenes, convincing the American military to release some of the magic detectors they had already in use for other purposes, to give it to us, and we would use it. And so, on the one hand, big telescopes could be built, equipped then over time with so-called adaptive optics to basically correct away the blurring by the turbulent atmosphere, which in the optical is very fast. At radio wavelength, you also have to deal with that, but it's typically minutes. In the optical, because of the short wavelength, it's a millisecond. So every millisecond, any phase you have gets changed by the atmosphere. So you have to basically measure that and correct for it. So that's a challenging electronics and optics problem. And then finally, of course, you want to make big telescopes. The Keck was the first one of these. The second one is the VLT. Today, there are more of these telescopes, but these are the two primary machines right now on Earth where we can combine large collecting areas and resolution. And the bigger the telescope, of course, in diffraction-limited operation, the sharper the images. Far, far, far from the event horizon, of course. I mean, we're talking here about not micro-arc seconds, but say 50 milli-arc seconds with a 10-meter class telescope. But, and that's been the last step, which we have undertaken with the 4 telescopes of the VLT, is to combine the optical light, very much like in radio astronomy, but now in the near-infrared wavelength, with adaptive optics first, so that we basically correct the images which are created by the single telescopes, and then bringing the light together, and then, like in radio astronomy, interfere the light, et cetera, et cetera. And as you will see, that has done an enormous amount of, given us an enormous amount of progress. So the work of the two teams here, Andreas Getz's team, Eric Becklin, Mark Morris, down in UCLA, and then we working with the VLT and initially a single telescope, and now with the gravity beam combiner, has been a real star in this show. The third thing I want to mention, definitely, is the same thing. Michelson interferometry, but this time to see gravitational waves. And of course, you know a lot about it, and I'll mention some of the results later on. I just want to point out, just imagine this. This simple thing, Michelson interferometry, is now at the forefront of 3 of the most outstanding astrophysics questions, high-resolution astronomy in the world. Only at different wavelengths or with different messengers. Now, the first cases, of course, the theory was introduced by Einstein in 1915 in Berlin. 1916, the first solution for steric asymmetric solution was found by Schwarzschild, and then a lot of good theory was created in the next 50 years about the question whether this event horizon, which showed up in Schwarzschild's solution, so a characteristic radius which only depends on the mass of an object, within which no matter or light can escape, so that there is a true break in the communication between the inside and the outside. But these objects are not just theoretical objects in a special symmetry case. So there was the next case of a rotating space-time. That was the Kerr-metric. Then charges were introduced. And finally, Roger Penrose looked at this problem more topological and basically showed that the event horizon is not a feature of specific arrangements of matter. No, it's a characteristic of space-time. If space-time has a more than a characteristic curvature, then you will get this phenomenon. Anyhow, the first cases came late. Galaxies are not black holes. Around us is, at least at that time, no black holes. Then came the discovery of the stellar, what we call now stellar black holes by X-ray astronomy. I won't talk about that. But then the first real case of these more massive variety were the quasars. The radio astronomers had been discovering new radio sources there. It is 3C273, third Cambridge catalog, and they had found objects which then on optical plates like this one looked like a meager little star. But star, I mean, obviously very compact. Yet in the radio, enormously powerful and variable, very, very rapidly variable. So, a bunch of theorists, among whose Lynden-Bell and Martin Rees stand out, but there are many others, then got to think about what could it be that creates the light in such an object from a small volume. And this is exacerbated by the fact that when you look at the optical spectrum of this object from Palomar, that was what Martin Schmidt did, you find that the optical lines, emission lines, are all very well known in their ratios, but all redshifted by 15%. Now, of course, at that time, it was already known that the universe was expanding, and that in an expanding universe, what's further away from you has a higher redshift. So you can apply that and calculate that this object, according to the redshift hypothesis, expansion of the universe, must be almost 3 billion light years away. That was, at that time, a super world record, A super world record. I mean, the universe at that time was a few millions of light years, so to speak. And all of a sudden, such a far and distant object. And then, of course, what looks like a meager little star actually is a very powerful object. If you calculate it, it's the equivalent of 1,000 times that of the Milky Way. 1,000 times. And all of this from a volume which obviously is not very large. So you put the numbers in, and then you see, well, that is something you cannot explain with fusion. Fusion in stars. It's just not efficient enough. But what it could do, what could be done, is to think of black holes. Now you would say, of course, what a nonsense he's telling me. First the black holes have the event horizon, and light cannot escape, and now they're supposed to. This fake news. Oh, maybe he would believe it. Actually, try. And basically, the idea, of course, is you're not looking at light which is coming from within the event horizon, but we're coming from objects, material, gas, sofas, cars, and everything else which is raining onto this central mass, attracted by its gravity, and thereby, converting potential energy into radiation. And that, near the event horizon, is a highly efficient process. Somewhere between 5 and 40%, depending on the rotation of the space-time. That's a factor of 1,000 more than fusion. So that was the idea. That was the birth of the idea. And the question is, well, how would you prove it? Of course, many people, observe these quasars now in the radio, X-rays, gamma rays. It's all very spectacular. I will that at all deny. But is it proof? Is it proof or not? And the answer is it's not, because the event horizon is the key thing. If you have a very massive object, which is a little bigger than an event horizon, and you let material fall onto it, you would get quite a bit of radiation out too. So what would we have to do? We would have to, in Gedanken experiment, measure the motions of this gas here and really right at the event horizon. That's the job to do, right at the event horizon, and showing that the speed there is, basically near the speed of light. Well, unfortunately, these objects are so far away that this, at the time for sure, seemed like a hilarious proposal. It's not possible. Cannot, at that distance of a quasar at that time, make a resolved measurement and then see something move. I show you today we can. Nowadays we can, but back then not. Well, Lindenbell and Rees knew the way out. They basically speculated that, well, these quasars are very rare. So that means they have a lot of accretion in order to be so bright. And that is probably not very common. And so if it's very rare, that means such quasars, or rather the phenomenon of quasars, that means accreting black holes, might be more common than we think, but fainter when they're in a lower state of accretion. If that is true, not only a few of these galaxies which harbor quasars, but maybe many, maybe all, have a black hole. That's what we nowadays think from empirical evidence. So by the 1970s, the train was already running. But the way to do the experiment was not possible. Because even if you look at a quasar, you would not see the motion. But then Lindenbell and Rees said, well, if there are nearby black holes, say, for instance, the galactic center has a black hole, well, then maybe you observers go ahead and check out the central region and observe what's happening there. Maybe you see something move, maybe at a fraction of the speed of light. He meant at the time mostly the hydrogen observers, H1, because that was the technology available at the time. That's not how it came to pass, but that was basically the idea. And then, of course, comes in Charlie Townes. Charlie, how should I say this? Had gotten this Nobel Prize, and his philosophy was always, Reinhard, you should do the following. You should enter a forest, which you don't know, then you should explore the forest, look at the trees and so forth, and you should get to know what's happening in that forest and understand and all of this. Write it all down, write a paper about it and so forth. And if you become famous enough, you will hear all of a sudden people behind you. That is the point, he said, where you have to leave the forest. And he's done that in his life, that he then left the laser research, became science politician for a while, and once that was done, he started to get really crazy and went west. You know, when you come from the East Coast, you understand if somebody, and that happened to me also when I said, oh, I will now go to California, Berkeley, and take a Miller Fellowship. They all looked at me. What are you doing? They're all crazy out there. Yeah, Charlie did it and opened up a new field of research, namely infrared astronomy. And he knew something about that from his laser work and his maser work. And he and others, I show you John Lacey as one of the many top students at the time who worked with him. And our friend here was participating in that also by building equipment. Walt Fidelson built instruments, the first instruments, to take spectra. Spectra in the middle infrared, around 10 microns, where you actually could look through the center of the dust lanes. You see the stars there in blue. The radio astronomers in the meantime had found a compact radio source named Sagittarius A star, here denoted by a red little dot. And then you see clouds. Green are neutral clouds, and pinkish things are ionized gas clouds. So Charlie and his team, with the spectrometer they had, took spectra like the one in the bottom right, And you see that these lines they saw in a spectral line of neon 2 at 12 microns were very broad and moved around from point to point to point. And if you look at the scale down there, 400, 600, 800 kilometers per second. Well, you know, we all know Newton, right? V squared R over G, that's the mass. Do this here, and you will find a few million solar masses. And Townes and John Lacey, when I arrived here, said, well, in the galactic center, Reinhard, there is a black hole. We will in the next years make more detailed observations from different wavelengths and different distances. And so we did. We then wrote a Nature paper in 1985 and saying, in the center of the galaxy, there is a big black hole. We didn't get a call. Nobody cared. Townes said, don't worry. But the rest of us, what's wrong? Well, what's wrong is very simple, really. We are looking at gas, and gas is not only a trace of gravity. It can be pushed around by stellar winds, by magnetic fields, and whatever have you. And also, the point at which the innermost measurements are taken here is at a scale of about 10 to the 7 event horizons. Well, there's a lot of space to put something else in there, starting with rocks and stuff. I mean, so most people say, come on. But the field then got started, and nearby galaxies were looked at with spectroscopy of the stellar motions, etc. So in principle, the evidence got denser and denser, and more objects were found, just according to this proposal by Lyndon Mellon Rees, that in fact these objects we now call black holes really are rather common. And that, and I will come back to this in the last part of the talk, their evolution are somehow coupled with the evolution of the galaxy. Now let's make a jump to our present time and make sure that we are on one line here. Some of you will say, what is he talking about? We know all of this. I mean, black holes. Yeah, of course, you can see this in every newspaper. Everyone knows it. It's not that simple. When I say experimental, I really truly mean, as I said before, spatially resolved measurements of dynamics detailing the space-time and showing that this derived space-time is really the same as that predicted by, say, the Kerr metric. And one way of putting this is in this so-called compactness parameter, where you see that in the bracket there, 2gm over rc squared, that number is equal to 1 if you have a non-rotating black hole. Then the spherically symmetric case for such a black hole, a non-rotating black hole, is epsilon equals 0. Anything else which is larger than a black hole, the R is larger, and therefore epsilon is greater than 0. So that is really what we have to prove. We have to prove that anyone can chip in and have ideas, and there are currently about 10 papers per week of ideas coming in of ideas. What it could be other than black holes. And you see some of the names there, boson stars, fermion balls, especially in Italy these days. Remo Ruffini is really quite adamant that what we're looking at in the galactic center is a fermion ball, and Grava stars, wormholes. Wormholes, I should say. I find myself giving these talks in broader public, and then comes the question, by the way, why is that what you're observing, not a wormhole? And what should I say? So my answer is, well, you see, I'm just an experimentalist. I don't understand. What would you say, Roger? What do you think I should say? He says, it's very simple, nonsense. Or he rather said rubbish. Yeah, British, rubbish. Yeah. So it's really, I mean, I'm making light of this, but it's really, so to speak, fairly impressive how, and that's their job, the theoretical community is coming up with good ideas, what it is, why it is not a black hole. And I think we should take that seriously. That's our job as natural scientists to make it better. Well, I have to admit, I mean, this movie it took a little long. It took 35 years to make that movie, and that's why we didn't get any funding anymore for it. So, but I mean, you know, who cares? We really did this. We are able to measure now the motions of stars on solar system scales in the central region. Here's the star both groups have been following for this long period, and you see it's in a highly elliptical orbit. Sagittarius star is that dot in the bottom. You see the half-light radius there is on the order of a fraction of an arcsecond, and it's in a highly elliptical orbit of 0.8. And at the nearest point, the Peri, the star is a mere 15 light hours away from Sagittarius star. That's about 3 times the orbital radius of Neptune. And there it has a velocity of about 7,500 kilometers per second. So you do the same thing, v squared r over g, and what do you get? Same formula on your solar masses. We could have spared ourselves all that work. I mean, you know, we knew it already in the 1985 paper. But okay, here that one was finally believed by almost everyone, and both groups obtained it, which is, as you will admit, very important. You know, if he says it's that, and I say nah, it's not. So we know the mass of the galactic center now to about 0.2% accuracy, and likewise the distance. And that will play a role in the next picture, because from that and general relativity, we can now predict certain parameters, which we can then test with other methods. Okay? And with the interferometry, we can now come so close that if we go on, we will be able, or we hope to able, to see effects of general relativity, like, for instance, the gravitational redshift, the precessions, that is the Schwarzschild precession and the precession due to the spin. So all of this is now in hand or about to be in hand. Also, let's start with the gravitational redshift. That effect, of course, is when you have a star or a light source moving around a black hole, and when it's closest to the black hole, then it takes more energy for the light to escape from the source and reach us, and that results in a shift of spectral lines, in the case of the galactic center, by about 200 kilometers per second. So Newton would here be a flat line, and the GR effect is red, so that is pretty good for government work. And yeah. And the next effect is the Schwarzschild precession. So if you recall your basic astronomy, if you have a star or sun and one planet orbiting stably around this sun, then the orbit will not be changing. So it can change if something else is around, but if nothing, then it shouldn't change. In GR, there are two precessions, one in the plane of the orbit, forward, and depending on the size of the orbit relative to the Schwarzschild radius, and the other one due to the spin of the black hole. And so if there were no GR, then in this residual position diagram, X and Y, in milliarc seconds, you see fractions of milliarc seconds, you should always stay at 0. GR gives that windy little loopy curve. These are the precessions. And the data which we have in hand are these. I would say not bad for government work, or A minus. Now, of course, we are still with this star, say, at 1,000 Schwarzschild radii. And you could argue, well, okay, it's fine, there is something massive and very compact, but it's not a black hole. So therefore, our goal has to be to come closer. And there are two ways we now have. One way is we're looking at the gas, the hot gas, which flashes up every few days for about an hour or so in the infrared, also sometimes in the X-rays. And when we look at this with the interferometer, what we see are these green points, which show a loop of points, which lasts, as I said, about an hour. And the speed, these arrows in black, is about 1/3 of speed of light, 0.3 c. And this radius of this region here is about 10 times the Schwarzschild radius. So now we're getting pretty close. And it always goes in the same way. You've seen now about 10 of those, and it always is clockwise. So there seems to be, Reinhard. There seems to be a preferred direction, and what might happen here is sort of a situation. We know that from the measurement of magnetic fields. It's a highly magnetized region where magnetic fields might collide, form a reconnection. Our space sciences people here will know everything about that, and they accelerate electrons to about 100,000 times the normal relativistic motions. And then you can get synchrotron emission from infrared or even X-rays. And the same process, in a way, you can also follow in the radio. So if there is a radio source behind the black hole on the left side there, when you observe that from the right, then it's clear that in normal non-GR physics, only the central black hole radius would be blocked, and you wouldn't see light coming through. But general relativity, of course, predicts curvature of orbits, which goes all the way out to about 2 times the event horizon size to be bent enough that they don't make it. And so the picture you should expect is a bright ring around a dark hole. There it is. That is what the Event Horizon collaboration published a few years ago. And so here's where I'm saying, here we have an absolutely fantastic, wonderful test. Per se, that image is nice. It's certainly consistent with general relativity, but must it be? That's, again, the question, must it be? And the answer is, well, we can predict what that size of that ring is from the mass and the distance. And how large should it be? 51 microarc seconds. Not bad. Now, of course, one would like to do this much better, but For now, what we can say is both the hot gas in the center as well as the EHD shadow experiment tell us that the same mass we have seen at 1,000 Schwarzschild radii also is present within a few times the event horizon size. So let me summarize this. When Charlie started this with John Lacey, they were beginning to take measurements at around 10 to the 7 Schwarzschild radii, and were seeing that the mass was not depending very strongly anymore on radius going inward. So that's what in 1985 we published. Okay, must it be a black hole? And then over the years, the UCLA group and our group have pushed this in and in from motions of stars and orbits of stars. So pretty good agreements there at around 1,000 times the event horizon size. And now the last step was these motions very close and the shadow of the black hole. And all of this is consistent with a single mass. A single mass. And a very important trick is that in the motion of the star, this loopy motion, we can measure the Schwarzschild precession. And the Schwarzschild precession and the precession of the star we measure are identical. That means that there is no so-called classical retrograde precession, which is due to an extended mass. So the mass which we are seeing here at a few Schwarzschild radii truly is a very, very compact configuration. And our friend Ruffini feels, well, he could still fix this with dark matter by having a massive enough neutrino, but honestly, in order to be that small, the neutrino has to have a mass of 540 kilo electron volts. I'm sure there are enough particle physicists in here who would say, and maybe that's equally important, this is just the galactic center. That's a little one. Let's go to the big black holes of the quasar category, 10 to the 10 solar masses. Scale that collapse mass there, and then that would mean that's absolutely impossible. So I would say to Remo, I say, Remo, I'm sorry, per Occam's razor, I think I make the conclusion that this is a black hole. We don't know whether it's a Kerr black hole. We have not measured the spin, and we don't know whether there might be near event horizon deviations. That's for my successor, Frank Eisenhower and his gang, when I'm already looking at the daisies, and I'll visit from time to time, and then I say, so let's see, Frank, what is the progress, Let me, one before I come to the, how much time do I have?
Another 15 minutes.
Good. Before I go to the cosmological questions, let me come to one more very interesting question here, and that's the so-called Bacall-Wolf cusp. So you go to any textbook in astronomy where you have a central mass, black hole or otherwise, and surrounding it a star cluster, and then you would expect, because of the interaction and transfer of angular momentum and energy, a cusp to form. A cusp where the density of stars to the inside gets bigger and bigger. It depends a little bit on whether you have a single mass stellar cluster or a multi-mass black hole, but the general idea is that. Now the reality is this. The very brightest stars, which we looked at in the 1980s, are these cyan stars. I mean, they show absolutely no peak toward the center. Then the next thing were the O and Wolf-Rayet stars. These are the black-yellow things. They show an increase toward the center, but then they drop again. So right at Sagittarius stars, not much. You go to the giant stars, the red stars, the most frequent ones, they are the red symbols there. They show a sort of a plateauing and a central plateau. The faintest giants we can now see are the green ones. They also don't show a peak. The only thing which shows a peak are these stars for which we saw these proper motions. And they are not on circular motions. They only dive in there, so to speak, bing, bing, bing. And so, and are not very many. So how come? In fact, if you plot the eccentricity of the motions, or 1 minus the eccentricity, so that means highly eccentric or parabolic orbits are on the left side, while circular motions are on the right side, versus the size of the innermost orbit, the peri-distance, then you see some of the solar systems units. You see what we can now say? We can say that the very massive stars, the red ones, they all are on somewhat circular orbits, but with a very large radius. None of them are close by. Whilst as you go closer, then you get these black objects, and the closer you go, the higher is the ellipticity. How can that possibly be? And that's one of the interesting theoretical riddles which currently we are working on with others. Generosov here has expanded on an idea which Tal Alexander and Hagar Peretz had already 20 years ago, where basically you take binary stars which happen to have a almost lost cone orbit, so almost parabolic orbit, and then as the binary comes close to the center, it gets so fast that in the interaction with the big black hole, one of the two stars gets more energy than the other, and shoots out of the Milky Way, and the other one gets stuck in a highly elliptical orbit. So that's perhaps the solution. The details of this are being worked out by a number of theorists right now. Briefly, let me say something about the gravitational wave work, which personally I think, and you will see that at the end, I feel will be the star of the show in 20 years from now. But right now, what the ground-based gravitational wave interferometers can do is look at stellar-type black holes or somewhat more massive objects. And the picture is about what one would have expected, namely a large abundance of objects which have sort of 20, 30 solar masses, which would be 10 plus 10 or something like this, right? But there are not an insignificant number of objects with more massive objects. Like, for instance, there is this GW 190521. That has a mass of 150, 160 solar masses. Now divide by 2, that's about 75. That is not a allowed outcome of a supernova explosion. Most of the stellar theorists would have said, well, such an outcome will lead to pair destruction. So you cannot have that. So it must be more complicated, obviously, than a single collapse to a then final intermediate mass black hole. And there's a lot of work going on right now. One would be, you have not only one, but several stages of mergers of such stellar black holes. Number two, like in the case of the massive black holes, you have accretion onto the initially not so massive, but then growing black holes. And a new kid on the block, again, last year at one conference for 1 week, 99% of the talks were on primordial black holes. And Raphael, do you know about primordial black holes? Yes. Well, we'll have to see. It's all incredibly fascinating. And experimentally, we have to look. if these are primordial black holes, well, then they should be elsewhere than the galactic nuclei. They should be elsewhere, and we should measure how many there are, et cetera, et cetera. So this will be observationally, obviously, an interesting avenue. Finally, then, let me come back to the big black holes, to the extragalactic big black holes. And we know from many, many observations that they typically are arranged. In the center is the supermassive black hole, and the surrounding is a very hot, highly ionized accretion disk. Surrounding that, a set of clouds called the broadline region, possibly or with some reason virialized, and surrounding that cooler gas, which many people have called the torus. So the key thing in the study of extragalactic black holes, if you want to do this like what we've done in the galactic center, is to use a quantity here spectrally, which gives you a width of a line, and therefore something in kilometers per second. And then the second quantity is the size of the region from which this line comes. And that would be an image. Now, that cannot be done, or could not be done, until recently directly, other than by timing. And that timing was a famous paper by Crisp in 1982, the reverberation technique of basically looking at the time delays between the variability of the central massive black hole and then the reaction of the broadline region. That has been sort of the standard technique and has given us hundreds, chunk pi, thousands of black hole measurements. But of course, allow me, I'm an experimentalist. I want to see this directly. And so we have been able to go to a step to expand gravity to phase reference to a star which is as far as 30 arcseconds away, and then look at a quasar. So this famous 3C273 we looked at before, there's the Paschen alpha line in the center there. You see the broad wings, that's the broadline region. And then below you see the east-west phase of the interferometer. And what you see is sort of an S shape. The blue side is negative, and the red side is positive. If you put this into an image that looks like on the right side there, the red clouds are below and the blue clouds are above, so to speak, and they are in a line which would be consistent with an edge-on disk. And the location of this disk is, interestingly enough, perpendicular roughly to this jet or coming from the central black hole. So that's what you would expect if you have a stable, virialized cloud system sort of broadly rotating about the central region. So that's a very nice case. Nowadays, and I'm going indeed to the situation we now have since JWST and new measurements with Gravity Plus. These are in blue. The JWST ones are in yellow. Of quasars in the redshift range 2 to 6. The ones which we see in the local universe, on the left side as well on the right side in red, is sort of a mass of 0.2, 0.3% of the galaxy mass is in the black hole. And it looks now increasingly probable, but I would say this is not final, that at high redshift, the black holes are, relatively speaking, more massive. By what factor? Well, it could be as much as a factor of 10 or 20. I would say this is preliminary. For the yellow points there, you cannot guarantee that you have a virial equilibrium. For the blue, we can, because it's the same technique I showed you. We will work very hard in the next years to push this to as high a redshift as we can, to test the question is how fast did the black holes grow in the early universe? And that is a very important question. Because if you plot the black hole mass versus time in a situation where you accrete material at a certain rate. Then you get here 3 different curves: the red curve, the black curve, and the blue curve. And you see they have labeled 10.1, 1.1 and 10 to the minus 3 Eddington. And that basically is so to speak, a measure of how much accretion you get relative to the maximum amount you can digest if radiation pressure doesn't push the material back out. And the classical picture was that that normal high redshift quasars should be the red line. So that means their doubling mass should be, basically on the order of a few by 10 to the 7, 10 to the 8 years. And if you start with a heavy star or a star cluster, you never will get to the 10 to the 9, 10 to the 10 solar mass class you're observing at high redshift. So many people are discussing now that there is much faster accretion. That would be that dark red line. At 10 Eddington, you could, at redshift 10, reach sort of the kind of quasars which we are now beginning to see with JWST and gravity. But of course, that is all a matter of future work, which I'm sure many people will participate in. The question of the seeds, namely what is there on the bottom left? I put it as the seed 10 to the 7. Well, pure imagination. What about if it's 10 to the 5? Well, then everything moves downward by that in logarithmic units. So we don't know what the seeds are. Are they particularly massive stars, very low stars? Is there the possibility of super Eddington accretion? Is it perhaps because the radiation efficiency is very low at low metallicity? And many other ideas which are being put down now and proposed, including the primordial black holes. Now, the primordial black holes have one difficulty, that the general idea of producing black holes right after the Big Bang is that these masses you would produce at very, very high redshift, it would be typically very small. And so then you would need many growth factors to end up at the masses here. We will see. And some of the younger ones may have a chance to make a career in this. Future prospects. Well, what about the spin? Well, we have one star, which you see there on the top left, which has an orbit which is 3-4 times smaller than the star S2. 0.94 ellipticity, an orbital period of 4 to 8 years. Wow. If that is true, and we catch it next time and next time, so that would be sort of a while away, then we could measure the lens steering precision and the spin. The radio astronomers want to build a bigger or better EHT to look at the substructure of their rings, which has information on the spin. With a machine for the ELT we are currently building, which has fantastic resolution and sensitivity spectroscopy, we could measure the first 5 terms of the GR factors. And finally then, LISA, which we talked about already in the bottom there, could measure the in-spiral of a stellar black hole into a supermassive black hole and get very, very high accuracy numbers on the quasi-normal modes. And you see the factor there, delta Q, that's what I called epsilon, of 10 to the minus 4. So if that's true, they would know. So it's a long way. It takes 100 years to get from Einstein's theoretical work to where we are now, but boy, was it exciting. Okay, thank you.
Thank you, Reinhard. You want to turn on the lights? Go for questions? Questions? Yes?
Hey, Mark, can you hear me?
Yeah.
Thank you so much for this very interesting talk. I have a pleasure of actually knowing 2017 about Vice Mayor Barry Shu, who of course is a distinguished person as well. And as most of you guys may know that Barry's work with LIGO confirmed the existence of gravitational waves, so directly detecting mergers of black holes. How do you see gravitational wave astronomy complement with your work on the supermassive black hole at the center of the Milky Way? And then real quickly, a quick follow-up on that question. Well, a quick follow-up is on a general question for young scientists. Since Barry and I actually are co-founder of World Young Scientists, or Mentors for Young Scientists, what's your advice to young scientists and entrepreneurs interested in pushing the boundaries of space exploration and astrophysics? Thank you.
Okay, well, so I did, although too briefly, talk about the gravitational waves, of course. And currently, the ground-based machines do not have the frequency coverage of looking at massive black holes. And that's why I mentioned LISA several times. I mean, LISA is going to be, for me, the thing of the future. And I would say for some of the young people, that will be, if everything goes well, that will be the place where we can actually make really excellent and even pivotal measurements of general relativity, the Monod-Hare theorem, and so forth. It needs a little bit of patience. The first time the current LIGO group came to ESA, I was on the selection committee, was in '92. And it took, until now and probably another 15, 18 years until Linda Tacconi up there had a similar experience as chief of the ESA selection committee with the radio astronomers. Also, the radio astronomers would say, give us a bigger machine and we can make still higher resolution measurements. And the problem is some of this is coming to limits which are what I would call close to the abyss of death. James Webb Telescope is actually in that limit. It really had luck that it survived. At this price level, we are open ourselves, of course, to the political forces fully. And if you hit all of a sudden a political force who says, no, absolutely not with me, do something better. I have more important things to think about, then that's the problem. But nevertheless, I would say LISA is an absolutely fantastic thing. For the young people, do whatever you find exciting. Do excitement is in it. If you would have seen Charlie Towns, he was in his last 1.5 years. He turned in the end not quite 100, which was what he really wanted. But here, the department he was in his 99th year, had a little party out there here in the summer, and Charlie was not well. He had pneumonia. He didn't even recognize me at that point. He didn't. It was really sad. And then he sat there in this wheelchair, and then the students came. And Charlie, within, 3 minutes, woke up, joked around, and talked. Immense. That is what, working with young people, having the excitement of science does to you, waking up from death.
So, more questions? Yes?
You touched on this a little bit, but I was wondering, what is something that you currently don't know but would love to understand?
Could you repeat the question?
Sorry.
Yeah.
You touched on this a little bit in your talk, but I was just wondering, what is something that you currently don't know but would really love to understand?
Many things. No, seriously. I mean, that is a question of, you know, there are people who are, you know, fantastic scientists and can think about everything. Chris is one of them, yeah. And I'm more modest. I can only do very few things, and I have to make a decision. And so if I want to do all of the things I could think of, well, then nothing will come out of it. So that's the other thing. Be excited, but also be a little clever, like Charlie, in which forest you go.
On your last slide, you had a table with, I think, five effects that you wanted to measure. I was wondering how do you measure the length during effect? Like, or what is the general process of doing that?
Sorry, I have not heard.
In the upcoming experiments,
Yes.
there was one with a table, and I was just wondering what experiment, if you could go into a little bit of detail on how that works.
Okay. You mean this table?
Yep.
Well, basically what this it shows for this instrument we're building for the ELT, which has a given resolution of 0.1 kilometers per second in spectroscopy. Now, if I make a measurement there and I have a certain error, and that's the error which you see below, 10 kilometers per second, 1 kilometers per second, 0.1 kilometers per second, then I get the following GR effect, Schwarzschild lens, Tearing lens, to these accuracies. Okay?
Would dark matter halos produce changes in the radial velocity on that order?
Well, that depends now, of course, where you are. I mean, this is the story throughout the talk. If you look at a tracer, which is produced yonder, then you cannot be so sure. But if you look at a star which really comes in very close, and then you measure the spectral lines to these accuracies, then you can be fairly sure, right?
Okay, thank you.
Okay. If there are no further questions, I'd like to mention that Reinhard will be here for another 2 weeks, so I'm sure you can still talk to him.